In this video, we're going to talk about properties of rational functions. So let's start by defining a rational function. So a rational function is a function of the form, so let's call it f of x. Okay, it's equal to p of x over q of x. So it's a fraction where p of x and q of x are both polynomials, and q of x is not the zero polynomial. So obviously we don't want to divide by 0. So the domain of a rational function is all x values for which the denominator, q of x, is not equal to 0. Okay, so q of x is not just exactly 0, but we need to throw away all the x values that make q of x equal to 0. Okay, so the domain has all the x values where q of x is not 0. Okay, now the rational function r of x is in lowest terms if p of x, the top, and q of x, the bottom, have no common factors. Okay, now one important thing to remember is the domain, okay, must be found before simplifying. So you want to take away all the things that make the bottom 0 immediately before you put the rational function in lowest terms. So let's see an example. So suppose I have I want the domain of r of x, and r of x here is x squared minus 4 over x squared minus 4x plus 4. So this is our p of x, which is clearly a polynomial. It's a quadratic polynomial. And this is our q of x, which is also a quadratic polynomial. So we're going to find the domain, and then we're going to write this in lowest terms. So to find the domain, we need to solve the bottom equal to 0. Okay, now this we want to factor, so I want two numbers that multiply to give 4 and add to give negative 4. So that's going to be x minus 2 and x minus 2, so, or minus 2 and minus 2. So x minus 2 squared is equal to 0, which means that x is equal to 2 would make this 0. Okay, so that means that this is the thing we need to get rid of. So the domain is x not equal to 2, or in interval notation, it's negative infinity to 2, not including 2, and then 2 to infinity, again, not including 2. Okay, so that would be our domain. So now when we want to write it in lowest terms, what we want to do is factor and see if they have any common factors. So the top is a difference of squares. So it factors as x plus 2, x minus 2. And the bottom we just saw factors as x minus 2 squared. Okay, now they do have a common factor. X minus 2 can cancel with one of the ones on the bottom. So r of x is equal to r, or x plus 2, divided by x minus 2. So now they have no common factors, so this would be in lowest terms. Okay, now we can only cancel, so this step to this step, if that term is not 0. So we need x to not be 2, but we needed that anyway, and we still need that at the end. So the domain of our simplified function is actually the same as the initial. Okay, but that doesn't always happen. So that's why you need to do the domain first. Okay, but doesn't always happen. Okay, so I'm going to leave example 2 for you to try. So you can only cancel common factors in the numerator and the denominator, not individual terms. So be careful about how you cancel. Make sure that you have factored it out before you try to cancel. So we've done transformations already on y equals 1 over x. So remember that looks like, so we have a vertical asymptote at x equals 0. And it actually has a horizontal asymptote at y equals 0. And then the graph goes through these points and looks like that. Okay, so that's the graph of 1 over x. Now what we want to do is add the graph of 1 over x squared. Okay, now this also x equals 0 is not in the domain. And it ends up that it's going to be a vertical asymptote. Similarly, we're going to have a horizontal asymptote at y equals 0. And then here, so if I plug in x equals 1, I get 1 over 1 squared. So that's still the point 1, 1. If I plug in x equals 1/2, so maybe I should do this. So x equals 1 gives me y equals 1. X equals 1/2 gives me y is equal to 1 over 1/2 squared. So that's actually 1/4. So I'd flip the bottom and multiply. That's actually going to give me 4. So that's up here. Okay, and if I plug in x equals 2, then y is 1 over 2 squared, so 1 over 4. So it's down here. So we actually get the same shape, but it's a bit stretched. So it grows a bit faster and shrinks a bit faster on this side. Okay, but that's going to be okay, those are some points. And then when we do it with the negative numbers, so if x is -1, y is going to be 1 over -1 squared, so that's also 1. So the square is going to cause us to have the same values as we do above. So in fact, maybe I should just write here, this is symmetric. Oops. Maybe I'll just write, so it's an even function. Okay, so that means it's symmetric about the y-axis. So these points are going to be the same in the same spots. And the graph is going to look the same on this side. Okay, so that's what it looks like. So that's the graph of 1 over x squared. So I'm going to leave you to do the transformation of that graph. Okay, so it works the same as normal. So all the regular transformations are the same. Yeah, so I'll leave you to do that example. Okay, now let's start talking. How do we know when there's a vertical asymptote or a hole? We haven't even seen a hole yet. So to define a vertical asymptote, so if the y values approach plus or minus infinity, so they get really large, as x approaches some number, let's say c, then x equals c, so that gives the equation of a vertical line, is a vertical asymptote. In the graph. Okay, so that's how we know. So the y values get really, really big. Okay, so here are some So these are the vertical lines, x equals c for some c. And our graph can approach in a variety of ways. Okay, so maybe on both sides the graph goes to positive infinity. Okay, so it might, I should draw it a bit better. So it could be that the graph, I don't know, okay, goes to positive infinity on both sides. It could be that on one side it goes to negative infinity, and on the other side it goes to positive infinity. Okay, it could be that they both go to negative infinity as we get close to c, or it could be the flip. So maybe on this side it goes to positive infinity, but on this side it goes to negative infinity. Okay, so those are all the different ways you can approach a vertical asymptote. Now, this is very important. Okay, so a graph cannot cross a vertical asymptote. Okay, so that never happens. So here's how we can tell the difference. So how do we know when there's a vertical asymptote versus a hole? So a hole in the graph at x equals r, if happens, so we have x minus r as a factor in the denominator. Okay, but if that factor can be cancelled so that it does not appear in the denominator in the simplified, the lowest terms, then we get a hole. Okay, and to find the y-coordinate, we're going to evaluate the lowest terms version at x equals r. Okay, now if it cannot be cancelled, that's when we get the vertical asymptote. Okay, so we describe the hole using the coordinates of where it's missing, and the vertical asymptote we describe with the equation of the vertical line. Okay, now I'm going to leave part A for you. So actually, another way you can sort of tell, so if you plug in x equals r, okay, if you get a number that's not 0 divided by something that is 0, this is telling you that you have a vertical asymptote at x equals r. Okay, now if you get 0 over 0, then that means that x minus r is a factor of both. Okay, so sometimes that's going to mean that you get a hole, okay, but it could still mean that you have a vertical asymptote. Okay, so you want to be careful. So just because it's 0 over 0 doesn't mean that you're going to get a hole. So for instance, I'm going to go back here. When we did this first example 1 here, so x equals 2 is not in the domain, okay, but if we try to plug in 2, we got 0 over 0, okay, and the x minus 2 factor on the top canceled on the bottom, but we still had the x minus 2 factor. Okay, so that means that here x equals 2 would be a vertical asymptote even though the factor canceled, because there was 2 of them on the bottom. So that means that it's still a problem, which is why we get a vertical asymptote. So at this point, if we plugged in x equals 2, we would get 4 over 0. Okay, so that's going into case 1. Okay, so that's sort of what's going on. So let's try 1. I'm going to skip A and B and do part C here. So this is our function. So it's x squared plus 3x minus 10 over x squared plus 2x minus 15. Okay, so we should first find the domain. Okay, so that means that we want to solve the bottom equals to 0. So we would factor it. So I want two numbers that multiply to give negative 15 and add to give positive 2. So that's going to be x plus, that's plus 5 and minus 3. Okay, so that's equal to 0 when x plus 5 equals 0, or x minus 3 equals 0. So that's x equals negative 5 or x equals 3. Okay, so our domain is x not equal to negative 5 and x not equal to 3. Okay, so we don't want, both of those are, there's no value in the graph. So now we want to decide, are they vertical asymptotes or are they holes? Okay, so what we want to do then is simplify, put r of x in lowest terms. Okay, so let's look at r of x. Okay, so we want to factor the top and the bottom. Okay, we already did the bottom, so we know that this factors as x plus 5 times x minus 3. For the top, I want two numbers that multiply to give negative 10 and add to give positive 3. So that's going to be plus 5 and minus 2. Okay, now we can see that the x plus 5 factor goes away. So the function is going to simplify to x minus 2 over x minus 3. Okay, now this last step is if, or maybe I should write as long as x is not equal to negative 5. So I can't cancel 0 over 0, okay, but for all other x's, I can cancel those values. So this is our simplified version. Okay, so notice that the x plus 5 in the denominator is not there anymore. So at this point, okay, so here we could evaluate at x equals negative 5. Okay, so what that tells you is that x equals negative 5, that problem, okay, is a hole in the graph. Okay, now because x minus 3 is still a problem, that means that x equals 3 is a vertical asymptote. Okay, so x equals 3 is a vertical asymptote, whereas x equals minus 5 is a hole. So when we want to find the coordinates of the hole, okay, so the x coordinate obviously is minus 5. To find the y coordinate, okay, we plug in minus 5 into the simplified form. So it's going to be minus 5 minus 2 over minus 5 minus 3. So that's minus 7 over minus 8. So it's going to be at 7 over 8. So that's the y coordinate of our hole. Okay, so that this is the plug x equals negative 5 into the simplified function. Okay, now the reason why we can do that, so you might be concerned because I said as long as x is not negative 5, and then I just went and plugged negative 5 in. Okay, so I'm not saying there's a point there, I'm actually saying there's not a point there. Okay, but I could plug in x equals negative 4.99999. Right? I can be as close as I want to negative 5 without actually being negative 5. And the values, so the y values are going to approach this value. Because if I'm really, really close to negative 5, I'm going to get a value that's really, really close to this number when I use the simplified form. And that will be a point in the graph. So basically, our function is this graph with just this one point pulled out of it. Okay, so that's what's going on there. So what about factors of the numerator? Okay, so if a rational function is in lowest terms, okay, and you have x minus r as a factor in the numerator, then there's going to be an x-intercept at r0. Okay, so for example, okay, in example, what is this for? Example 4. Part C, okay, the simplified form is x minus 2 over x minus 3. So that means that there's going to be an x-intercept at 2, 0. Okay, so because x minus 2 is a factor in the numerator. Okay, so that's when the top is 0. Okay, so this x-intercept makes the top of my function equal to 0. So when you have a fraction and the top is 0, that's when you get equals to 0. When the bottom is 0, that's when you get something undefined. Okay, what about horizontal asymptotes? So here, if the y values approach some fixed number, let's call it L, okay, as x gets really big, so as x approaches plus or minus infinity, then y equals L, so that's the equation of a horizontal line, is a horizontal asymptote of the graph. Okay, so they've drawn some here, so these are the equation y equals L. Okay, and then there's some, how could we approach this? Okay, so maybe the graph is fully below, okay, the horizontal asymptote, so you might get something like this. It might be fully above, okay, the asymptote, or you could actually cross the asymptote. So you could have something like that. Okay, or something like that. Okay, so it is possible to, so in contrast to the vertical asymptotes, you may cross a horizontal asymptote. Okay, so that is possible. Okay, because you're only talking about what happens as x is large, it doesn't really tell you anything about what happens when x is small. Okay, so it's possible that you can cross a horizontal asymptote, so you want to try and remember that and not let it freak you out. Okay, it is possible. So how do we find horizontal asymptotes? Okay, so for rational functions, there is a rule you can memorize if you want. So when you have your rational function, p of x over q of x, in lowest terms, okay, you can find the horizontal asymptote by comparing the degree of p versus the degree of q. Okay, so if the degree of p is smaller than the degree of q, then you get a horizontal asymptote at 0, y equals 0. If the degree of p is equal to the degree of q, then your horizontal asymptote is the leading coefficient of p divided by the leading coefficient of q. Okay, so, and then the final case, which is not in here, so if the degree is bigger on the top than the bottom, then you don't have a horizontal asymptote, you have what we call a slant asymptote or a curved asymptote. So that can still happen. The asymptote would be the quotient when you divide p of x by q of x, okay, but it's not horizontal. So we're not going to talk about it in this course. Okay, so for us, you only have a horizontal asymptote if the degree on the top is smaller or equal to the degree on the bottom. Okay, so let's do an example. Okay, so I'm going to do part A here. So find all horizontal and vertical asymptotes for the following. Okay, so we'd want to think about this as in factored form. So the top is going to be x minus 2. For the bottom, I want two numbers that multiply to give negative 24 and add to give positive 2. So I think that's plus 6 and minus 4. Okay. So for the vertical, so nothing cancels, so this is simplified. So that means the vertical asymptotes are going to happen when the bottom is 0. Okay, so x plus 6 times x minus 4 equals 0 when x plus 6 is 0, or x minus 4 is 0. So that's going to be x equals negative 6 or x equals 4. Okay, so those are both our vertical asymptotes. So x equals negative 6 and x equals 4 are both vertical asymptotes. Okay, and then for our horizontal asymptote, it's going to be at y equals to 0. Okay, now the reason for that is the degree of the top is equal to 1. Okay, that's the power of the x, which is less than the degree of the bottom, which is 2 because it's a quadratic. Okay, so because the degree of the top is less than the degree of the bottom, we get the horizontal asymptote at y equals 0. Okay, I'm going to leave parts B and C for you to try. And that is all we're going to talk about for now for the properties of rational functions. In the next section, we're going to take this further and actually try to use these properties to sketch the graph.